Hello and welcome to our 26th lecture, Introduction to Integrals. We're zooming through the math chapter, approaching physics chapter, so it's about time we get serious. Don't worry, integrals are not as hard as they sound to be. Well, they are difficult, but like learning all that we will learn in the following 3 lectures, they should be no problem for you, at least on the basic level, for what we will need later. So, integrals surely sound scary, but we have technically worked with them already, if you believe it or not, because integrals are really just a fancy name for summation, adding stuff. So we remember this, right? The sum of all a's. So the I here is like the number that starts with 1 and increases all the way to n, and we just add up all the terms. I think that's called a sequence. I forgot, doesn't matter. We've been summing stuff up before. Hopefully we remember this. So integrals have the same idea, but instead of adding terms, we add infinitely many extremely small parts, so we get our formula. Integral of function of x times dx, which we remember from derivatives from last time. So basically, we multiply the dx part to the function, and that's all in the integral, like this giant mess. Dx here means those small changes, and we are adding up the segments of the function, but more on that after terminology. So this is the difference. So we see the sigma notation, the sum notation, is like steps, so each extra term adds a step, while integral notation is like a smooth curve, because the infinitely small parts can create a much smoother curve than flat pedals would. Pedals, levels would, whatever the word is. Oh, I did add the meme. So yes, the integral sign seems like a big S, and S stands for summation. Yes, coincidence? I think not. Maybe it is, I don't know. Anyway, terminology. So this is how integrals are written very often. We have the curved symbol. It's called the integral symbol, on top and the bottom of which you write the limits, the upper or top limit. I will use the top limit because it's easier for my brain, and bottom or lower limit of integration. I will get to these two near the end when we cover the finite integrals. Then, but yes, this sign is followed by the function we have, and it's called the integrand, however you want to remember it. And that function must have a dx added after it. So x here represents the variable of the function, which is the variable we are integrating, as we will see an example later where the function isn't present and how that behaves, but also we will solve many examples next time and when we learn how to actually solve them. But yes, as we can see here, dx is written in the same fraction level as the function, so sort of like it was multiplied to it, while in derivatives it was closer to the function being divided by the dx, so we can speculate that the integrals will do the opposite job than the derivatives do. But if we look at the definition of the derivative, we know that it's a slope of the function. So what would the opposite of that be? Well, I think I already said it before. I'm dumb, my memory don't work, but I don't know if it's indeed opposite, but integrals represent the surface between the x-axis and the graph. So let's think a bit. So let's say derivatives and integrals are the opposite, so that means if we take a derivative of some function, we find its slope. But if we integrate it, we're supposed to get the surface under the graph. We know that the surface under the graph will increase or decrease, depending on the y value that the graph has, more importantly, how fast that the y value changes per 1 x unit. So that means the function's behavior, so change of y from change in x. Like here, the y went from end of blue to end of yellow, and so did the x, and that decides the change of the surface. Let's say the surface under the graph doubled, so like this is surface 1, this is surface 2. Let's say they're equal, while this sketch is not proportional, but like let's say they're equal and this doubles. So that means that the amount of change to the surface is determined by the function at that point. So quote unquote, slope of the change of surface would be the function itself. Well, that's basically it. That's hella overcomplicated. I genuinely zoned out while I was speaking, so let's see another example on the right here. It shows white and yellow segments, areas between the graph and the x-axis. I forgot to mark the axis, but I hope you can forgive me for this. Integrals have this sort of annoying property, which makes sense but can still cause some problems to people learning them sometimes, that the surface below the x-axis, so on the right is colored white, will count as negative surface. However you want to visualize this. So in this case, the first yellow part and the white part later cancel out if they're the same. So the integral of this entire graph shown would equal to only this small yellow half, which I circle in blue. This is only for the finite integrals where you have the limits, like I said before. We will also cover infinite, where there is no limit, and that's basically the function that describes how the surface changes. But yeah, we will see how this makes sense in the following lecture, but also if you pay attention today, you may be able to figure out how this sort of shows. Oh, and Wikipedia also shows it very nicely. Basically plus, minus, plus. Okay, so integrals in an equation form are written like this. So the integral of some function of x times dx, or differential of x, is equal to the capital F of x, and this part is called the antiderivative, or a primitive function of the function of x. However, this isn't the exact correct equation shaped formula yet. There is one thing missing, and that's the one thing many students forget. That is c, or the constant. You can do plus c minus c, just have to include it there. So the integral written here is the indefinite integral. That's because it doesn't have the limits, so the upper and lower numbers on top of it. Because it doesn't have them, we must write the plus c, as we will see later in the video, and more clearly next time, when we learn how to solve them. But yes, so that all stems from the logic that with derivatives like 2x plus 1, taking the derivative of that with respect to the x, the result is 2. So the 1, so the constant, disappears, and when integrating, this c stands for any constant that might have disappeared. It's either determined from the task you have, or it's a finite integral, to which we will get later today, and you will see that the c disappears. So remember, kids, don't forget your c's when integrating. So let's see an example why we need c. So we have two functions here that we will take the derivatives of. First is x cubed plus 5, and the second is x cubed plus 3. Using the power rule, we get the following. We see we get the same result, so we know that their slopes change the exact same way as x increases, but how do we differentiate between these two functions? Like, let's integrate 3x squared. If so how would we differentiate the result of the integral, so the antiderivative, so the result of integration of this, from the function if it has plus 5, plus 3, plus 0, or even minus 247? Well, we can't. That's why we add a plus c after integration like this. So our integral of 3x squared, we know it's x cubed. We can use the power rule in reverse, which I will explain later. And we get x cubed, and then we add plus c. So for the first example, the c would equal 5. For the second example, c would equal 3. And that's basically how you solve these examples to determine if this function falls in the same family as the integrals of this function. I think that's how it's worded. I kind of forgot. I think there's one thing on the mini test in this regard, like kind of style. So yeah, this process I'm showing you on the screen right now is using something called a Riemann sum. If this exists in limit towards infinity, we would call that a finite integral. I think this is some oversimplification of the real thing, and to be honest, I don't really know this topic that well. So if you are interested in it, or like in why and how it works, you're more than welcome to read up more on the topic. But I think this isn't really that crucial for us, as yes, it is quite important to define it right. We are mainly using these lectures to learn how to use stuff and why we use the stuff we do in a way that later on we can reference and understand why certain stuff works the way it does. Okay, so we're in PhET again, the same link as last time. And we're using the integral part. So last time it was derivatives, now it's integral. We see on top is gonna be the graph of the integral. On the bottom we have a function. So let's say we move this slightly higher. The sum, let me just, yes, here. So once we reach the peak, this is like the halfway point. Then we still have like this surface under here to add. Once we add that, the surface here stops changing. And it's gonna keep doing the same thing. I don't know what this is, but okay. It's gonna stay constant. So the surface between the x-axis and the graph stays constant because this is at 0, roughly here. If I move this part lower, it's gonna subtract, as you can see on the top. It's gonna subtract from the overall sum. And if I move it back up, oh, there we go, that's high. If I move it back up, it's gonna like launch up. I'll just like add stuff, add peaks, and I can just like drag one lower so it subtracts. It goes even into negatives. So you kind of like see how this changes. I could also like, oh, this is like a plateau. The overall behavior, okay, sure. So you can see how like here the graph, let's say by here, this green resembles the surface area under the graph, and this is like the numerical value. So this is, I don't know, 15 units squared. This y-axis is like, has the unit of units squared, if that makes sense. So basically, the integrals represent the surface, and its behavior changes like this. Hopefully this was helpful. You can also play around with this. It's called Calculus Grapher on PhET Colorado down in the bottom right corner. Okay, so that was it from me doing PhET simulations. And yes, so integration is basically reverse differentiation. So latter also known as finding the derivative. So since we don't know any rules or the integration table, we will just use the differentiation table and use it in reverse and always add the plus c at the end. And of course, here is the table just in case some of you have forgotten it. But from now on, I will expect you to either remember these or at least look up the table yourself if you need to use it. For this lecture, I will be giving snippets of it. So we'll essentially be trying to find an integral of the right side, and the left side will be our result for all intensive purposes for today, of course, because we don't know how to actually integrate just yet. So for example, integral of 0 would be c. Integral of 1 over, 1 over x would be natural logarithm of x, plus c in every case, of course, etc. So for our first example, we have an indefinite integral, so don't forget the plus c, of 4x squared dx. The dx will always be present in integrals, so let's find the table. So our integral is the part on the right side, meaning to get the left side, we must increase the exponent by 1, and then the new exponent, we have to divide by that new exponent to get rid of this n part in front. So we increase the exponent by 1 to get, because 2 represents n minus 1. So what is n? N is 3. So x to the power of 3. And then we divide the entire thing with 3, because that's the new exponent, and that's the n value. So 4x cubed times 1/3, because we divide by a 3, plus c, of course. And that gives us this. You can also differentiate this and see if we did it correctly. So we reduce this exponent by 1. So we have x to the power of 2. And then we multiply by the 3. So we have 4 times 3 divided by 3. 3 cancels out. It's 4 times x to the power of 2. And the constant, since it doesn't have the variable, disappears. So yes, this is correct. Time for a trigonometric example. Integral of minus cosine of x dx. So these are our two derivatives from the table that could be related, but we see that on the right side we don't have a minus cosine. So we do the next best thing and we analyze it. We know that the minus only changes the sign of y result, meaning the slope at any point will just be the opposite value, well, especially here. So does that really change the surface between the graph and the x-axis? Well, it shouldn't, since it's all it's doing is mirroring it over x. So let me just draw. So let's say this is our cosine, very scuffed one, and then we change it and then just multiply it by minus, so we get minus cosine. We get something like this. So the overall surface, like the absolute value of the surface, should be the same roughly. So while this is the +1 and +1, and this one is minus, and they just keep canceling it out. But this one starts with minus, continues with plus, etc. So the only thing is this, like, the surface technically stays the same, but just minus is in front of it. So like the opposite sign in front of the surface value, if that makes sense. So it turns out that this is correct to just put the minus outside of the integral because it changes the surface. Yes, but we will learn why that is from the rules next time. But this throws us back to the start with yellow and white graph. Here with minus, we just change the sign of the integral value. So if we were to start with positive values of cosine x, we would start with negative on a minus cosine of x, etc. But their behavior basically stays the same, just the opposite, twisted around, whatever you want to call it. And this would give us the minus integral of cosine of x dx. And now we do have something in our table, so we will just group this and install our solution. So we have a minus and then a bracket of sine of x plus c. Of course, the plus c could stay inside of the bracket as well and then become a minus c, but then again, the constants have a certain value. They would just be written differently. So if it's written here as minus c, then the resulting constant would be negative. I don't know, I just prefer it plus c because it's easier to determine the signs, because minus minus is a plus, while plus minus is minus, and you just leave minus. Basically, why overcomplicate stuff when you can do it simply? I said now, however, I always overcomplicate stuff, because why not? But yes. Again, don't forget the C, because I definitely didn't forget a few while making this PowerPoint and then frantically edited them last second. So, as we will see in physics, there is something called a triangle trick, which we can use with the derivatives and integrals as well. Well, with markings present. And it's basically when you have a product of two factors and you get a third one, that one is on top, while the two factors are on the bottom. So let's take a formula for velocity we saw last time. Velocity, v, equals s divided by t. We can form the triangle from this, or I can rewrite it so it's easier to show. So some s equals v times t. Now let's get the triangle done. So this is a triangle, and these two multiplied values are written on the bottom. And then we will insert the last one as the result on top, like this. Oh, wait. Okay, that doesn't matter. So if we need to know the formula for either of these, we take that one out, like, so basically circled with red, and that one equals the rest. So if we want velocity, we take it out, and we're left with s on top and t on bottom, and that kind of looks like a fraction, so we have a fraction of s divided by t as the result. If we wanted to solve for time, we would take time out, and we would be left with s over v, so divide the path we covered with the speed we had on it, and we would get the time it took for us to drive that path. If you wanted the path, you would just circle that out, and we would be left with v times t because they're on the same level. So, but how does this apply to our lecture? Well, let's see. So we know that the antiderivative marked with a capital F is the marking for the function that is the result of integration of lowercase f. So since I don't like the integral sign here, I'll just remove it, but change the capital F to df, since this means if we move this dx to the right, so divide both sides with dx, we would get the differentiation of the, this is how we write derivatives. So like it's written in the second row. So now this allows us to draw the triangle from these three elements: functions, antiderivative, and the differential of x. Because, well, we see here, if we take a derivative of this, we just get like this. Differentiable form, however you want to call it. Basically, yeah, something like this. I forgot what I wanted to say here, I think. But yeah, because we were differentiating, the constant disappears. And now we have three factors we can insert into our pyramids. We have a fraction, so the top part goes into the top part, the bottom part goes into one of the bottom slots, and the result into the left one. Or with the product, this one is on top and these two are in the bottom. And this is our pyramid. So to be fair, I only thought of this slide because in an elective course that I have on university, we were deriving something called Young-Laplace equation, which describes the pressure difference across a fluid interface, like that of a bubble or a droplet. So the surface, the pressure difference between the inside and the outside, or however that is. But the important part is, there was a step, we have some change of volume marked as dV, and we replaced it with the derivative of it, like its derivative is the surface of the bubble, I think, and dr at the end of it. So it's just something I found useful to mention, so don't beat yourself up too hard if this is too complex. It's just a nice, a bit more advanced approach to solving stuff. But yeah, it shows how they are the inverse processes. And of course, if you do integrate, so if we do not remove the sign or have d in front of capital F, we must add a plus c. But hey, anyone can be great at maths and physics if they can just push through and accept that a lot of the time progress will look like solving hard problems that make you feel like you're stuck. Because like you have progression that you can track when you're discovering new terrain. So like digging a hole. Going down the hole is not progress. Digging it out is the progress, and that thing requires physical work and exhaustion. So again, this is a finite integral as opposed to the indefinite one without the limits. Yes, which will look like this when I have more than just it on the slide. So again, b and a are the upper and lower limits in the integration respectively. F of x is the integrand, d of x is the variable of integration, and capital F of x is antiderivative, and we see that the constant isn't present. And we will see why in just a few slides. Unlike indefinite integrals, definite have, the finite, whatever, they have limits, as we can clearly see. And if we know that the integrals refer to the surface under the graph, the limits must have something to do with the boundary conditions or boundary points. So let's take a look at the graph. This is another example from BYU's learning app site. We see that the yellow marked area represents the solution to the integral written on it. So the integral between the x values of a and b. But is there another way that we could write this mathematically in a bit easier way to solve? Like, since integration is a sum, maybe we could write it as a sum, product, or maybe even difference? Yes. If we think integrals represent the sum of all tiny changes of x under the graph. So if we look at all the small changes between the two limits, we could solve for the surface under the graph in the limit. We could solve it by getting the integral, so the surface under the graph up to the upper limit, so everything that I have poorly marked with the red marker, and then subtract the integral, so the surface, up to the point of the lower limit, which I have marked with blue. And since the surface before the bottom limit is present in both, the integral of upper and the integral of lower limit cancel out this blue part, and we're left with the yellow, so the space in between. So I will do a written example so it's slightly easier to imagine. So if we say we add up all the elements until the upper limit, called b, which is, I don't know, valued at 6, we would have the sum of the first 6 elements. And if we had a lower limit at a equals 4, we would add the first 4 elements. Then if we took a difference between them, all the elements from a would also be present in b, so they cancel out, leaving only the elements between a and b, so present in b, but not present in a. I could do this all with sets, but it would overcomplicate stuff, so I'm just gonna draw it. So we see that there's like a few elements in a, a few elements in b, because, well, counting up to b, that kind of makes sense. Yes, there's b number of elements in b, and there's a number of elements in a. Kind of, that's a very poor example, but like, these would be the result of the integral between b and a. Kind of. Hopefully this visualizes it, but yes, this brings us to our formula for the finite integrals. We get the antiderivative, so the integrated function, in which we insert b and a and take the difference between the two, and we get our result. As you can see, there is no plus c part here because that constant represented the family of functions that could have been differentiated into the one we integrated. Complicated words. However, here we have a specific numerical interval, so between a and b, and we're looking at an individual function. And that function would have the same constant term, which would then cancel out as c minus c0. So when we integrate this, we get a certain function, let's say x cubed plus c. If we insert the b value as x, we would get a b cubed plus c minus a cubed plus c, because it's the same function we're inserting the value in. Just like with the limits, remember when we had the function where we inserted h into x and then we subtracted just the f of x. So only the h present terms existed, remained, whatever you want to call it. Basically the c's cancel out, leaving us with an actual result, a number. Technically, you would first write the result as just the integrated function of x, then a straight line after it with limits fit upper and bottom limit to show for this, and then write the difference, but that's an intermediate that we will leave out and focus on the integral and the solution, as that one won't bring much more to an understanding, but if you want to know, the bottom line is how you would write it. And I colored it dark orange just so you can see, but yes, for this we do need to know how to integrate, so this is our integral. We have the limit between 0 and 2. Our function is 3x squared dx. And we solve not for the function of integration, but an actual value, because we have boundaries, whatever. Oh god, I'm repeating it like a broken record, but like if I don't, I may say it one time's too few and someone won't remember. So again, let's solve for the surface under the graph. Now we will use our power rule in reverse, so we raise the exponent by 1. We divide by the current new exponent. I multiplied by inverse because yes. And then mark the bounds, which is done with a vertical line after the result of integration, and then just like upper and lower limits. Plus we can use brackets to make it easier on ourselves. And now I simplify because 3 divided by 3 is 1. And then we get 2 to the power of 3 minus 0 to the power of 3. Which is 2 to the power of 3 minus 0, which is 2 to the power of 3, which is 8. And this is our answer. There are 8 square units under the graph, well, between the graph and the x-axis. So if you use the length between two consecutive x values as 1 unit, there would be 8 square units under the graph, again, between the x is 0 and x is 2. So now that we have covered derivatives and integrals, I'm sure you guys have had plenty of interactions with this small fellow. So what even is this? I've called it differential of x, I call it dx. Well, in math we aren't technically supposed to insert the x value in it, but in physics we will, sometimes. So what's it all about? Well, firstly, it does stand for differential of x, and it's basically a limit of delta x when x approaches 0. You will see that later, don't worry. Usually we don't insert the values in the, like, delta x. Like, delta h represents the difference of heights and stuff, like manometers for pressure measure. But dx, we usually don't. Like, oh, actually, sign for velocity is v, while d of x or delta x, or delta h, is the sign for something. So we don't insert the height into it. That is the height itself, or the change of height. It's like, remember back when I said that anything can be a variable, even a whole word or a sentence, if you like write it in the right way. Any symbol, any scribble can be a variable. So dx can be a variable, delta x is a variable, and it's different from normal x. So, yeah, physicists sometimes insert the value. Don't ask me, I'm a chemist. But secondly, well, we do know it represents an infinitesimally small change in x. So the change of x variable. So I guess we could kind of visualize it as a nudge to a person, an item, a micro correction of an angle in steering. Oh, I drew something later. So, but yes, we will run into many examples of small changes in physics, so don't worry. However, modern calculus just viewed it as a part of the notation, so like a plus sign in addition, sort of. And of course, on topic for today, it marks the variable for integration and differentiation, so you can integrate or differentiate with respect to time, radius, position, dilution, etc. So x will be replaced by those quantities. So not by the values, but like differential of radius would be dr, for instance. Hopefully this clears out some confusion, as seeing a variable that you can't fill in with the value of it does feel annoying, but with this, hopefully you can start seeing it as a notation rather than an element. Hard to speak. So while on topic, let's compare the finite delta x and the infinitesimal changes, differential of x, or in other words, between the difference between the differential of x and delta x, or if I want it to be funny, delta of x and differential of x, ha ha ha. Math people may get it, or they will say how stupid this was. Well, anyway, so finite change is marked with delta. And its value is that of the difference between two values. It can be big, small. For example, today, by the time of making this slide, which is like 3 days ago, we solved an example in class where delta h, so the difference in height, was 78 meters. Quite far from a small number, right? Similarly, difference between values of the function with two different values inserted can also be marked with delta, which we will get when we work with pressure? I think, yes, under pressure. On the other hand, the infinitesimal change marked with dx, or differential of x, I just like dx because it's faster, it represents a small change. Usually we don't insert the value of x into it, as then we would get a differential of a constant, which is 0. However, let's imagine something. I'll do my best to draw it with my mouse. Let's say this handsome stickman is pushing a block of dark blue ice for some reason. Let's say that with all his strength he manages to move it for 5 whole centimeters, which let's say is a relatively smart length compared to the size of the ice block. So I grayed out the all position to show the moving, so in this case the value 5 centimeters would be labeled as dx. So we could also label it as L, like length, or C for change, whatever you want to call it, with one letter, but it's more accurate to represent it with this because it's a change of x dimension. For instance, if you have a cube and you enlarge it along one side, you write the cube's coordinate as like x plus dx, y, and z. Don't worry, we get to that in physics. So yes, 5 centimeters is a small change relative to the size of the block. Of course, the change could be greater, but then delta x would be more fitting, as technically they represent the same value, but the concept is different. Dx is for small values primarily, delta is for any change whatsoever. That's why in physics, sometimes delta x will become dx, so we know we're working with small changes, which will allow us to integrate, differentiate, etc. Basically, any change can be marked as delta of the value, but d is sort of reserved for smaller changes, especially if we're gonna use it for differentiation purposes. Now, to learn about multiple integrals. Don't worry, that was a joke, well, mostly. This is another one of those previews or optional topics I present that, while they aren't as common, are still good to be familiar with. In this case, while this does sound absolutely terrifying, trust me, I was terrified when I heard that a subject I have as a mandatory course in chemistry has triple integrals. It's actually not that hard. Trust me, as someone who's not that smart in math, this is not... kinda. If we imagine a single integral as the sum of super thin lines under the graph, we can imagine double integrals as the sum of small rectangles, and triple integral as the sum of small cubes. Kinda. So for a double integral, for example, we see here that we have one and a function, and then another one. So we simply decide to solve the innermost integral first, only integrating for the variable present, so y here. And then between the 4 and 6 for the boundaries, for change of y. We integrate and insert, and we get the difference of two terms. Now we integrate that difference of two terms, so this becomes a new function. We integrate that for x. So in this case, these were able to be added together. We get a new function. We integrate this function to get the result, and then insert the values, and then blah, 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 blah. So it's basically like L'Hopital's rule. You apply it, you solve. If you're not done yet, apply it again, etc. Solve for one integral as far as you can. When you can't anymore, solve the second one, the third one, etc. Of course, we need to learn the rules to solve them. So this may seem hard now, but believe me, you're capable of learning this. I genuinely believe that almost anyone, just by watching through my videos, can solve integrals. Just if you really apply yourself, this integral here, easy. You could solve it as an appetizer. And just for fun, or for those of you who want to actually learn or test your knowledge, using the reverse of the power rule, try to solve this for homework. As I said before, solving examples is the best way to study, so I recommend it. But if you're stuck, the solving process is done. So the solving is done by Coven Academy, and the video is titled How to Solve Double Integrals Steps. Well, this brings us to the end. Here is our mini test. Hopefully everything was understandable. If something wasn't clear, please comment down below. Suggestions, whatever you want. I'm always open to suggestions and feedback because I always look to improve. But yes, thank you so much for tuning into this lecture, which was actually quite long today, goddamn. And I'll see you all on our next quest. Bye.